Good afternoon, everybody, and good morning, Youngsoo. Today with us, we have Youngsoo. Youngsoo is a research staff in the Center of Applied and Scientific Computing at Lawrence Livermore National Laboratory and is leading the data-driven modeling team in the laboratory. And today he will give a talk about where are we with data-driven surrogate modeling for various physical simulations. Please, Youngsoo.
Oh, thank you so much for the kind introduction, Maria. As Maria introduced, today I am going to talk about surrogate models for various physical simulations. I know that CISA has very strong research group on surrogate modeling or reduced order modeling. So I'm sure you will be very familiar with what I will present today. So please listen to my talk to find out what sort of surrogate modeling projects are going on in Lawrence Livermore National Lab. After my talk today, I'm hoping that we can collaborate in near future. Some brief outlines of the talk today. In the beginning, I will introduce two types of surrogate models, non-intrusive and intrusive surrogate models. Then I will start to give examples of non-intrusive models first, and then switch gear to intrusive surrogate models, so-called reduced order models. Okay, as you all know, we live in an exciting time. The machine learning and artificial intelligence keep surprising us with its capabilities and improving the convenience of our daily lives here and there. For example, I believe you all remember the machine learning-based Go player, AlphaGo, defeated a top professional Go player, Lee Sedol, from my home country, actually. That was scary, personally. Artificial intelligence did not stop its advance there. Now, machine learning and artificial intelligence is enabling self-driving car and advanced speech recognition. But for now, I don't think that you want to sleep in a self-driving car. But in the future, the technology will continue to advance, and for sure, you will be able to sleep in a self-driving car someday, right? All these were, by the way, applications where first principles hardly exist. So people thought and imagined, I think they still do, that machine learning and artificial intelligence will completely replace computationally expensive physical simulation models that have been developed for about 100 years now. That has not happened yet, but I'm sure many researchers like us will keep trying and be successful someday. However, I would like to emphasize in this talk that you may want to incorporate the existing first principles in your machine learning when you try to build machine learning-based physical simulation model. Anyhow, this endeavor can be summarized by two words, that is surrogate modeling. Let's give motivation for surrogate models first. You are looking at a beautiful simulation modeled by smooth particle hydrodynamics for shape charge penetration. The simulation is well matched with experiment, but very expensive. One fold simulation takes 7.4 days using high performance computing facilities at Lawrence Livermore National Lab. This is unfortunate in multi-query applications, as you well know, such as design optimization, optimal control, inverse problems, and uncertainty quantification, right? So many researchers have tried to build an efficient surrogate model that accelerates these kind of simulations without losing much accuracy. Another motivation can be given due to the climate change. Temperature is increasing, and therefore the ice in Greenland is melting and sea level is rising. In order to better predict and possibly prevent the disturbing rise of the sea level, we need an accurate ice sheet model. For example, this ice sheet simulation for Greenland takes 16,000 cores and 1.12 billion degrees of freedom and takes 400 seconds for one time step. Typically, you will want to run the model for decades and centuries. And there is a pretty restrictive CFL condition for this problem. So imagine how expensive it would be for one-fold simulation, right? If we talk about the inverse problem, where we need to find out, for example, basal friction and ice thickness, many fold simulations needs to be run. Furthermore, if we talk about some Bayesian optimization setting where uncertainty needs to be incorporated, this is simply intractable. So we need surrogate models to accelerate these kind of simulations. Surrogate model can be built by first considering a parameter space D. The parameter space can be initial condition, boundary condition, or material properties of climate modeling, for example. Then you collect data by solving full order model for several sample points. Then you apply machine learning techniques to build a surrogate model. Various machine learning techniques are available as listed here: proportional decomposition, canonical polyadic decomposition, Gaussian process, generative adversarial network, etc. So various surrogate modeling types are possible, as you can see, but depending on how much you incorporate physics laws in surrogate models, it can be intrusive or non-intrusive. I will go over some disadvantages or the advantages of intrusive and non-intrusive methods later, but for now, the procedure goes on. Using the surrogate model, you can accelerate simulations with various query points here and there, and many more which you haven't used in your training phase. These surrogate models can be categorized by its level of intrusiveness. For example, black box approach, denoted as BB, is the least intrusive method, requiring only data. Then we can think of more intrusive methods. First, the linear subspace reduced pseudo model, so-called LS-ROM, where the state fields are represented by compact linear subspace. And even more intrusive methods, that is nonlinear manifold reduced pseudo models, so-called NN-ROM, where the state fields are represented by compact nonlinear manifold. Roughly speaking, more intrusiveness means more accuracy, so reduced order models are more accurate than the black box approach if the same amount of data are used. On the other hand, more intrusiveness means less speed up, so the black box method is faster than reduced order models in general. Okay, now let me give two different but somewhat similar black box non-intrusive approach, that is linear multi-step neural network and deep fluid. Both of them directly approximates the state outputs, by the way. And they follow the same framework where you start with the simulation state data here and compress the data into low dimensional latent space, right? And then reconstruct the full data by decompressing them. For the compression, there are many dimensionality reduction techniques. In general, they can be divided into two categories in terms of the reduction type. One is the linear subspace representation, and the other one is nonlinear manifold representation. Okay, the first black box approach I would like to introduce is the linear multi-step neural network. This work is done with Jessica Lajon from Stanford. This method uses linear subspace dimensionality reduction approach, which is POD. To demonstrate that, let's say we have airfoil flow data here, depicted as W. We use singular value decomposition to obtain a reduced basis for the state variable, then project the original airfoil flow data W onto the subspace spanned by the reduced basis and obtain the reduced data A here. Then the linear multi-step neural network is trained using the reduced data A in order to propagate in time in the reduced latent space as depicted here. Then the full state is restored by the reduced basis phi, As you can see, we have only used data throughout the whole process. The no governing equations were involved. So it is definitely a black box approach, but directly approximates the whole state field, as you can see. We have applied this black box approach for the flow around airfoil simulations. Here we change the Mach number to compress data using singular value decomposition and train the linear multi-step neural network. As you can see, that the predicted surrogate model and full order model solutions are identical in eyeball norm, while the surrogate model takes only 2.55 seconds, but the full order model takes 314 seconds, giving us a speed up of around 100 times. Quantitatively, the relative error is less than 1% everywhere. Not bad, right? Okay, the next black box approach I would like to introduce is deep fluid. The methodology is not invented by us. It's from Youngsoo in Switzerland, where the nonlinear manifold learning algorithm, that is autoencoder, is used for compression and decompression of the solution data W. In autoencoder, the encoder compresses the input data to latent space, as you can see, and decoder decompresses the latent space data to obtain an approximate full state solution. The overall autoencoder parameters are trained by minimizing the difference between the input and approximated the full data. Once the autoencoder is trained for the prediction, we apply latent space integrator to propagate in time in the latent space. Since the size of the latent space is small, this time integration will be very fast, as you can imagine. Then with the predicted latent space solutions, we restore or reconstruct the full state by applying the trained decoder. We have applied this black box approach to Berger's equation, where the simulation is very advection dominated and shock front is formed and moving, as you can see from the movie. The full order model and the deep fluid solutions are very similar in eyeball norm, while the deep fluid gives a speed up of greater than 100. Quantitatively, the deep fluid gives the maximum relative error of 38.6%. This might be a bit too large depending on the applications you are dealing with. So later in the talk, I will show how to reduce this error tremendously by applying a intrusive method, which is reduced order models. Now let's switch a gear and talk about linear subspace reduced order model. Next 2 to 3 slides, I will go over some technical background on reduced order model, although most of you are familiar with this, but in case there are some folks who are not familiar with this, I will go over some technical background and then introduce some variants and their successful applications in various fields. All right. Here, I'm going to introduce the projection-based reduced order model approach. To do that, we will start with this governing equation represented by the ordinary differential equation. Here, W is your state variable, F is your nonlinear function, and T is your time variable, and mu is your parameter. We first approximate the solution as linear combination of reduced spaces phi. Again, you have seen this before in previous example, and whose dimension is a lot smaller than the full order model dimension, big N sub S. Then you plug this solution representation into the governing equation, then you will end up with an overdetermined system, as you can imagine, where you have more equations than unknowns. So to close the system, you apply some kind of projection. Here I have applied the Galerkin projection, but some other projections is possible also. But at the end of the day, it gives a reduced system of ordinary differential equations to solve. Then you can apply your favorite time integrator to this reduced system. Here I have applied the backward Euler time integrator just for the demonstration purpose. This gives us the fully discretized reduced nonlinear system of equations you have to solve in every time step. Now you see there is a nonlinear term f in the equation here. Every time the argument of the nonlinear function changes though, through the Newton type iteration, for example, you have to update the nonlinear function and multiply it by phi transpose. Unfortunately, this scales with the full order model size. It turns out that if you solve the reduced order model in this way, it is actually most of the time slower than the corresponding full order model. So what is the point of introducing this reduced order model if the process is slower than the full order model and it only gives an approximate solution, right? So people have developed a technique called hyperreduction to reduce the complexity of the nonlinear function. The most famous hyperreduction technique is DEIM. I'm sure you agree with that, which stands for discrete empirical interpolation method. The DEIM introduces the nonlinear basis phis of f and then express the nonlinear terms as a linear combination of nonlinear basis vectors, as you can see here. Then it introduces a sampling matrix Z, which selects an important subset of the nonlinear terms. So after the action of Z on nonlinear term F, only the subset of F will be evaluated. Now the sampling indices of the matrix Z can be obtained through various algorithms. DIM and QDIM are popular ones. Then the generalized coordinate for nonlinear term F of hat can be obtained by solving the interpolation problem, right? Then you plug this expression into the reduced system of equations wherever the nonlinear term shows up. Then you will end up with these crazy looking equations, but if you look at them close enough, most of the terms can be pre-computed. And this nonlinear term can be effectively computed thanks to the sampling matrix Z in front of it, right? If this is how no, I'm sorry about that. Okay, this is how we achieve the efficiency through reduced order models and the hyperreduction. There are many variants of DEIM, for example, GNAT and SD-GNAT, but the main machinery of the hyperreduction follows this paradigm that I have just introduced here. This kind of linear subspace reduced order model has been successfully applied to many problems. You are looking at the captive carry simulations done by Kevin Kalberg, who used to be my former boss, who is now in Facebook. And here you're looking at the pressure field on the left and vorticity field on the right. Top result is generated by reduced order model, and the bottom result is generated by full order model. In eyeball norm, they look identical, but reduced order model takes 32 minutes with 2 cores, while full order model takes 5 hours with 48 cores, which gives us 229 CPU time speed up. Pretty good, right? However, in spite of these successful applications of the linear subspace reduced order model, it had some major drawback. Let's look at the simple pure advection simulation where a rectangular pulse simply moving from left to the right. Unfortunately, the current linear subspace reduced order model cannot represent the solution span of these simple simulations. It is not hard to see that why. It is because individual snapshot data from the pure advection simulation is linearly independent to each other. So there is no way for the linear subspace basis to be able to represent the solution span compactly. Simply, you must include all the snapshots in the reduced spaces to accurately represent the solution span, which is unfortunate. In order to address this issue, we have developed a time-indowing reduced order model. The idea behind the time-indowing reduced order model is very simple. Because you need to include all the data if the simulation is advection dominated, you divide the time domain into several, as shown in the picture here. Then for each time window, you can build a local reduced order model. That way, each local reduced order model size will be very small and will accurately and efficiently represent the advection dominated solution, right? Once all the local reduced order models are constructed in the online phase, depending on where the simulation is in the time domain, it invokes the appropriate local reduced order model and use it to propagate in time. The idea is very simple, as I said, right? Okay, we have applied the time-indowing reduced order model to Lagrangian hydrodynamics seed of blast problems where the blast occurs at the corner and the shock is advected to all over the computational domain. The full order model and its data are generated by the open source code Lagos. Check it out, it's pretty good code, it's in GitHub. And the full order model has kinematic degrees of freedom of 14,000 and energy degrees of freedom of 4,000, and it takes 400 seconds for one fold simulation. It's not bad, but with the reduced order model, we can do better. As you can see from the movie, both full order model and reduced order model solutions are more or less the same. For the reduced order model, if no time-indowing approach is used, then it can still capture pretty good accuracy, but it is slower than the full order model as we expected. However, if the time-indowing approach is used, then we can finally achieve a speed of 4.6 with reasonable accuracy. If somehow you don't like this accuracy, then as I said before, the reduced order model can be tuned for a better accuracy. For example, you can increase the number of samples or increase the basis size and improve the accuracy, as we have done here. Of course, the reduced order model is not useful if it can only reproduce what the full order model has already produced in the training phase. So in order to see the predictability, we have varied the initial blast energy and see how our time-indowing reduced order model performs. As expected, it is the most accurate where the model is trained right here. That is the blast energy of 0.25. Then away from that point, the accuracy deteriorates as shown in this graph. This tells us that each reduced order model, the local reduced order model, has some trust region. For example, if you are okay with a relative error less than 1%, then the trust region of this reduced order model would be around roughly from 0.1 from here to 0.4 there, right? Okay, next reduced order model technique I would like to introduce is the space-time reduced order model. The space-time reduced order model tries to reduce not only the spatial degrees of freedom, but also the temporal degrees of freedom. It does that by introducing both space and time reduced bases. Excuse me. They are combined through the canonical product to represent the whole space and time solution space. Then the coefficient corresponding to the space-time basis vectors are the only unknowns, which maximally reduces the total number of unknowns. Then the space-time solution representation is plugged into the space-time formulation and form an overdetermined system. This overdetermined system is closed by taking the norm of the space-time residual and minimize it. This is the Petrov-Galerkin projection, as you can see. Then we apply the weighting matrix G bar to achieve the efficiency through the hyperreduction technique. We have applied the space-time reduced order model to a large-scale particle transport problem, whose problem size is around 10 billion, both in space and time domain. We were able to reduce that 10 billion degrees of freedom to only 10 and still gets the pretty much the same physics response as shown in the movie. The full order model took 17.4 seconds with 256 cores, which is not bad. But the space-time reduced order model was able to finish the simulation within 0.006 seconds with only one core. That gives us a wall time speed of around 3,000. And quantitatively, the relative error was less than 1% throughout the time history. Again, the reduced order model, the space-time reduced order model I just introduced is useless if it cannot predict the solution for new data point. Here, this numerical example demonstrates that our space-time reduced order model can predict the solution for various parameter points, which were not used in the training phase and still maintain the relative error of less than 1%. Okay, before I go to the next, here is the space-time reduced model, the paper, the Youngsoo and Karen developed. They were able to implement the whole process of the training, building, running the space-time reduced order model within 120 lines of Python code. So please check this out. This archive paper, it's submitted for the journal publication. It's under review right now. So this demonstrates that the space-time reduced order model I have introduced in previous slides, it's not that complicated. So please do not panic. Okay, the next, I would like to switch the gear again and introduce a new type of reduced order model, still linear subspace reduced order model though. Okay, just to give you a motivation, despite all the successful stories of the reduced order models that I have shown so far, as the full order model size increases, as you can imagine, the cost of training becomes very expensive and sometimes not even possible because of the memory issue. Also, if the parameter is spatially distributed, that is often the case in design optimization problems, in topology optimization, for example, then the dimension of the parameter space becomes too high to be tractable. Therefore, we looked for an alternative approach and found the component-wise reduced order model, so-called CW-ROM. The method deals with a small size of data, so the training cost is greatly reduced. Each small reduced order model components can be assembled like Lego block to form a system reduced order model. This is ideal for multi-components, multi-physics, and domain decomposition simulations. Okay, briefly speaking, CW-ROM first collects component full order model solutions in parameter space. For example, first collect data for the hat basket, here, 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 here. Then a part of bottom parts here. Then rest of the bottom data are collected separately. Then you apply machine learning techniques for each component and build first ROM and second ROM and third ROM. Then assemble the component ROMs to form a system ROM using first and second and third reduced order models, and then accelerate and predict the solution here and there and many other points. It's right. So that's the basic idea. But if I describe this component-wise reduced model in more concrete example, let's say we are trying to analyze the lattice structure design problem. Let me explain how we did that in this example. First of all, we built two component ROMs, the joint ROM and the strut ROM here. Then introduce very important concept called the ports, which is an interface that talks to environment. It connects with other component ROM. It can be used to impose the boundary conditions. Of course, you can add more components through an available port. It can be used to apply external force. You can even rotate the component and attach to the system, and attach many more as you wish to form your desirable system domain. Then in design optimization, we assign a density variable to each component, which varies from 0 to 1. Usually we avoid 0 to ensure the well-posedness. So we set our low bound to be 0.01. A small density variable implies putting no material there. Density of 1 means you put the material there. We automatize this procedure by solving design optimization problem to find an optimal lattice structure, for example, to minimize the compliance of the system. So here is a actual numerical examples of the lattice structure design using the component-wise reduced order model. Here we minimize the compliance imposing a constraint of mass being at most 40% only. The downward pressure force is applied on the top middle port here, and the usual boundary conditions are imposed at the bottom. The full order monolithic finite element solve, which is the most accurate the numerical method, involves 2.7 million degrees of freedom, while CW form has 30,000 degrees of freedom, like after the static condensation. And then CW ROM has only about 3,000 degrees of freedom, introducing reduced port basis. The movie, I hope the movie is gonna play. No, oops. Okay, let me try again. Okay, the movie, no movie. That's too bad.
It does not work.
Yeah.
Seems not.
Okay. How about this?
Yes. Now
I can manually. Yeah. Okay. Great. I can manually control the dynamics of the design optimization process. All right. In this movie, as you can see from here, the color is changing, and it starts from the uniform density, represented by this blue color. And then as the design optimization progress, it shows the red color with some, oh, it is actually working right now. Okay, so automatically. I don't know what happened, but the red structure is representing the density variable with 1. So you put the material there. So that represents the optimal lattice structure, given this pressure force and Dirichlet boundary conditions, achieving only the 40% of the mass and minimizing the compliance of the structure. In other words, maximizing the stiffness of the overall lattice structure. This optimization process is done by the method of moving asymptotes, so-called MMA, which is very popular in topology optimization setting. We were able to obtain the optimal lattice structure design within only 30 MMA iterations. Okay, let's look at the computational cost comparison. We have increased the port dimension from 8 to 62. The total degrees of freedom in the port was 62. So 62 port basis dimension corresponds to CW form. It's the accuracy of the CW form is the same as the conforming finite element method, right? The high fidelity models. We also compare with monolithic finite element approach just for fun. As we increase the port basis size, the computational cost increases for sure. For this particular numerical example, the CW ROM achieves 660 times speed up with respect to the monolithic finite element solve, while it achieves the 70 times speed up with respect to the CW form. Now let's see the accuracy of each case. The smallest CW ROM achieves a relative error less than 1% with respect to the full order model. So that is still pretty good for a lot of engineering applications. But if you don't like that accuracy, of course, the reduced order model is, the accuracy is tunable. As we increase the port basis dimension, the accuracy improves exponentially, as you can see from here. Okay, lastly, I would like to introduce the nonlinear manifold reduced order model, which I found it really cool. Okay, what is the nonlinear manifold reduced order model? All the reduced order model so far that you have seen so far has used the linear subspace solution representation, which lacks the capability of representing, for example, advection dominated simulations. This is mainly because the linear subspace solution representation is not rich enough, as I explained before. So it is not avoidable to think about, instead of linear solution representation, linear subspace solution representation, nonlinear manifold solution representation, right? And this is what we did in nonlinear manifold reduced order model. By the way, this nonlinear manifold reduced model has been introduced by Gukjin and Kevin 1 year ago or 2 years ago, but their method was actually slower than the full order model. So our contribution here is making that fast, so which I will explain soon how we did that. Okay, anyway, coming back to the discussion, here is the governing equation you have seen before, right? We approximate the solution as usual with some approximation. Now we introduce the nonlinear manifold, which is represented by the nonlinear function G here. That maps a small latent space dimension to full order model dimension. The nonlinear map is obtained through the autoencoder training with the solution data from the corresponding full order model simulations. Note that decoder is mapping the latent space to the full order state, right? From here to here, right? So it is perfect for our nonlinear map function G. So we use the decoder of the autoencoder as the nonlinear map function G. Then we plug this nonlinear manifold solution representation into the governing equation and obtain the overdetermined system as usual. So you have to close the overdetermined system. There are two different ways. The first one is applying the Galerkin projection to obtain the reduced ordinary differential equation, and then discretize in time to get fully discretized nonlinear system of equations. And then another the projection approach is least square pattern of Galerkin method, where you discretize the time derivative first by applying some time integrator and get the fully discretized system of equations. And then we applied, and then, you know, by, for example, by applying the backward Euler time integrator, and then close the fully discretized overdetermined system by taking the norm of the residual and minimize it. Again, as you can see, many crazy looking terms can be are there, but they can be pre-computed. And thanks to the sampling matrix in Z, in hyperreductions, you can work only with the sampled rows through the hyperreduction. But in nonlinear manifold reduced to the model, we gotta be careful. And so I would like to draw special attention to the structure of the neural network in the autoencoder, because the structure matters for the successful hyperreduction. Let's first look at the neural network with the two hidden layers as a decoder. And let's say that the orange disks in the output nodes are selected by the hyperreduction, the sampling matrix Z. Then if you trace back in order to evaluate these outputs, as you can see, the involved hidden nodes are increasing as the number of hidden layers are increasing. So at the end of the day, not much computational, the gains you get, even though you apply the hyperreduction in this, the deep neural network structure. On the other hand, if the self-net, if the neural net has is shallow, meaning that if you have only one hidden layer and sparsely connected, then finally you can get an efficiency through the hyperreduction with these selected outputs, because in hidden layers, not many hidden nodes are involved to compute this the selected outputs. Okay, here we compare the performance of various surrogate models in an advection-dominated 2D viscous Burgers equation, which you have seen before. But as you all know, it's a hard problem for reduced model to achieve a good accuracy. As you can see from the movies, MM-ROM and full order models are almost identical in eyeball norms, while LS-ROM, the traditional reduced order model, shows fictitious oscillations in front of the shock wave. The black box approach looks okay in eyeball norm, as you have seen before, but as you have seen, the actual relative error was around 38%. But on the other hand, NM-ROM achieves, excuse me, NM-ROM achieves a less than 1% maximum relative error. Furthermore, a considerable speed up was achieved by NM-ROM thanks to the hyper reduction we have developed. Okay, I would like to conclude the talk with some summary. I have introduced some surrogate techniques. I hope you found it interesting. And data-driven and physics-informed was the key words. I'm sorry. Okay, the examples I have shown you is the non-intrusive surrogate models for airfoil and the black box approach applied to Berger's equations and time windowing reduced Dodo model applied to seed of blast problems and space-time reduced Dodo model that achieves around 7,000 speed up for large-scale transport problem and the component-wise reduced Dodo model for lattice structure design. And finally, the nonlinear manifold reduced Dodo model that finally achieves a speed up of with a great accuracy for advection-dominated simulations. I hope that you have enjoyed the surrogate model techniques that I have introduced today. I'm eager to apply these techniques to many other physical simulations and hope to initiate some collaborations with awesome people at CISA. So if you're interested, please let me know. Well, and with that, let me conclude my talk. And thank you so much for listening.
Thank you, Youngsoo. Thank you for the beautiful talk. So now it's question time. If you have questions, you can unmute yourself and ask directly to Youngsoo your questions. So let's see if there are questions. Francesco.
Hello, hi, Youngsoo.
Hi, Francesco.
Thank you for your talk and also for an interesting seminar series about data-driven physical simulations. I'm really enjoying it. And I would just have a couple of questions. First, do you think that with your nonlinear manifold technique, you can achieve a better accuracy in the uncertainty quantification, in some uncertainty quantification problems with respect to purely data-driven modular reduction? And the second question is if you think it's feasible to extend your methodology also to 3D unstructured meshes. So with the autoencoders that involves graph neural networks or other convolutional structures.
Okay, so I will kindly ask you again to ask me the second question again, but let me answer your first question first. The nonlinear manifold reduced model I have introduced, I believe that it, it's a pro and cons. I mean, I cannot say that one approach is superior to the other, but okay, nonlinear manifold reduced model is superior to the purely data-driven approach in a sense that it will require less data than the purely data-driven approach because it is physics-informed through the reduced model approach. However, I mean, I cannot denounce the beauty of the purely data-driven approach. As long as you have enough data, once the purely data-driven approach is set, it's super fast. I mean, it's like the simulation is, like that, right? In real time. So, but it requires big data, and it does not, recognize the physics underlying physics. So, if you need to extrapolate outside of the training regions, it will do poorly than the physics-informed reduced Dodo model techniques, such as the nonlinear manifold reduced Dodo model. So I would say there are pros and cons in those two methodologies, depending on your applications and the level of intrusiveness you are willing to go into to develop the reduced Dodo model. Because I mean, in implementation-wise, it's quite intrusive. So otherwise, the purely data-driven approach, it's not that intrusive at all. You only need the data. So depending on your situations, I would say you choose, right? But there are pros and cons, right? Okay, so what is the second question?
Thank you.
It's the unstructured mesh, yeah.
Yeah, if you think you can, how you would extend this your methodology to 3D unstructured meshes. So in this case, in your burgers 2D case, I think your mesh was structured. Yeah. I don't know if you have in mind to something to extend it to more complex cases.
Right. So for example, I hope this
also considering hyperreduction.
Hyperreduction, yeah, exactly. So I mean, none of the the nonlinear manifold reduced model is limited to the uniform mesh, as we although have applied only the 2D Burgers equation with the uniform mesh. But I'm unfortunately, okay, this movie I'm trying to show is, oh, not this one. Okay, I'm showing the wrong one. Okay, this one actually, that's what I'm trying to show. So there's an underlying mesh. Initially it is uniformly uniformly discretized, but it's Lagrangian hydrodynamics. So as the simulation goes on, the mesh is deformed and the mesh is moving with the field, and it's quite complicated. Although for this problem, we have only applied the linear subspace reduced model, but there's no limitation. I mean, there's no, you know, the bottleneck for that the nonlinear manifold reduced model cannot be applied. I mean, it's perfectly applied, and as a matter of fact, we are working on extending nonlinear manifold to these types of problem right now. As we you know, produce some results, and I will happy to share with you.
Thank you very
hopefully
much.
Soon. No problem. Thank you for the questions.
Let's see. Okay, Giovanni has a question.
Yeah, I might have a question. Yeah, thank you very much, Youngsoo, for the really nice presentation. I have a question on the last part on the nonlinear manifold reduced order models.
Yeah.
It's let's say mainly a kind of a technical question.
Yeah.
Because I understood that you need to keep track of the activation path of the neuron in order to have a sort of hyperreduction. So in order to really compute the value of interest only in certain, let's say, locations of the domain which are corresponding to a certain activation path. I was wondering how difficult it is to implement such a, let's say, a computational strategy in an existing neural network architecture or in an existing code. And I was wondering which code did you use or
right. Yeah, thank you for the questions. It's always good to go into some details in the technique side. And as you mentioned correctly, once the hyperreduction identifies some selected outputs denoted as this orange disk here, for given trained neural network. Oh, by the way, we use the PyTorch to train the neural net, the underlying neural net. Okay, so and for given trained neural net with the autoencoder, and as you can see, we have to identify, we call it subnet, right? Which involves, you know, the hidden nodes, which involves to compute these selected outputs, and we apply a the mask operator in order to extract those the subnets in the hidden nodes, and build the corresponding dense operator corresponding to that subnet, right? and then just get rid of all the other the nodes and the connected nodes in the hidden nodes. But we found that if the neural net has a deep, the layer structure, the size of the dense, the matrix corresponding to the subnet is big, still big, right? So no hyper reduction advantage we obtain. So that's why we had to move from the deep to shallow and sparsify the neural net, and then apply the mask and extract the dense subnet and get the efficiency we need through the hyper reduction.
Yeah, and if I might, I have let's say another question, which is still on the same problem, which is somehow going in the direction of what Francesco has already asked you, I understood that if you go towards, let's say, a deep architecture, basically you lose all your computational efficiency, because
Right.
basically you need to compute so many activation paths that basically you completely lose the efficiency.
Yeah.
I was wondering if such a shallow architecture works also for let's say high dimensional meshes and possibly, let's say, unstructured meshes, and if you have any experience on this on, let's say, larger problems.
Right. Yeah, I mean, that's what we are heading to right now. If you are looking at, not this paper, this is the conference paper, but there's the archive preprint we have published, and it's under review for the publication. But there we used the two different the numerical examples. Well, actually, this 2D example was the larger scale problem, and the other example was 1D, the purely nonlinear convection problems. There, we found that as we as we increase the problem size from 1D to 2D, and we found that the performance of the NM-ROM was actually better. For the 1D problem, NM-ROM was only getting speed up of around 2, something like that. But for the 2D problem, we were able to get the speed up of 11. And we also did the back of the envelope calculation in the preprint, which I don't have it right now. I wish I can find the link and share it with you. But in that paper, in the back of the envelope calculations, it shows that as you increase the problem size, the NM-ROM will achieve a much better, a much higher speed ups with the good accuracy. So we are hopeful. That's why we are, moving to the larger scale problem right now. Yeah.
Okay. Thank you very much. Really interesting.
Thank you. Okay.
Okay. Francesco has a question.
Yeah. If I may, I have a couple of questions.
Mm-hmm.
The first one, I think it's slide number 30. So it was the slide in which you had the graphical summary of CW-ROM.
Oh yeah. This one?
Exactly, this one. So it's a curiosity. So in item number 1, you solve this component full order model, and in doing this component solve, you would need to replace the action of the other components by some boundary conditions. And
yeah, exactly.
Depending on the model, it might be tricky to set these boundary conditions. So what is your the recipe that works for you in your problems?
Right. Yeah. So we haven't invented. I should have emphasized that we haven't invented this component-wise reduced model. It's invented by the Tony Patara in MIT, and they call it Scribe, SCRBE, and there they use the pairwise, the training procedure. So for example, you identify some component to build a reduced model. So for lattice structure design problems, the joint component and struct components are identified. And then in pairwise training, you think of all the possible combination of the attachments between these different components, right? So for example, you have a joint component and the strong component, and you attach them together. And in order to find out the snapshots at the interface where they attach together. Okay, so for example, here in pairwise training, so you attach those two components, and then you apply some random boundary condition here and there, and then you solve the system of equations, right? And then you will get the snapshot here, right? And use that snapshot as a data, and you apply some singular value decomposition and truncate them and obtain the plot basis on that interfaces. So that's how they do it. But of course, the component-wise reduced model they have invented is only applicable to linear problem for now, for obvious reasons, right? For the nonlinear problem, it's harder. You lose the assumption of the linearity, which they strongly used in their the component-wise reduced model formulations. For the nonlinear one, it would be harder to obtain those the efficient data for at the interface, and the representation given by those data will not be enough to capture all the nonlinear response of the equation, right? So it would be challenging. So in that problem, I would think that it's unavoidable to think about some adaptive the basis approach, where your basis has to be the change as you explore the nonlinear manifold of your solution space. And also, even the nonlinear manifold reduced model type of approach might be better suited to extend the component-wise reduced model to nonlinear problems, because the nonlinear manifold reduced model, it has such a rich representability within that representation, because it introduces nonlinearity. So all sorts of possibility is out there, but the concept is such a beautiful concept, and yeah. So I think a lot of good research will come out of along this line of the thought, the component-wise reduced model. Yeah. So to answer your questions, the pairwise training is possible for the complicated problem. I believe that even triple, or the more the small scale, the assembled size, the training needs to be done in order to obtain good data to build the port basis, for example. Yeah.
Thanks. If I may, I have another question on a different part of the presentation. Probably slide 19, when you were presenting this time windowing approach. And yeah, my question is, how would you make it robust to parameter changes which affect the time scale? So I could easily come up with a problem in which by changing the parameter, maybe most of the most interesting part of the dynamics happens at the very beginning for one parameter value, and for a different parameter value at the very end of times. What ideas would be possible to use to make, say, a parametric robust version of this time windowing approach?
Yeah. I mean, so the concept is very simple, as I said. You just introduce the local ROM for each time domain. And we do have some parametric reduced model algorithm laid out in our first paper, which we are in the close to finalizing the paper right now, and then submit it and put that in the archive within 1 or 2 weeks right now. And there, it's the parametric ROM approach, like a global ROM approach, where for each local ROMs you train them. I mean, we relying on the collecting the data from the monolithic, the time marching, the flow model, right? So we collect them by varying the parameter for some given parameter in the beginning or at the end, and get the data, and chop those data into different time domains, and then build and combine each to extract the data from each the time domain with the parameter variations, right? And then just simply apply the singular value decomposition and hope to get the parametric ROM for each time domain. That's what we have done. So that line of the thought is the following the global ROM, the parametric strategy, but there are so many other parameterization techniques. You can build a local ROM, not just for the time domain, but also for each the parameters. You can decompose your parameter space into several subdomains, and then you build a local ROM for each parametric subdomain. And then as you explore that parameter space, you can go from one local ROM to another local ROM, right? So that's another the parameterization technique. And another one is interpolation. First introduced by David Amsalem right now, who moved to Facebook, unfortunately, so who is not doing any research on the reduced model, but his idea was pretty nice. You have a reduced order operator for these parameters points, and another reduced order operator for another parameter points. And in order to find the reduced order operator at the intermediate points, you interpolate the operator directly, but you do the interpolation in a sense that the property of the operator is maintained by doing the interpolation in appropriate matrix manifold. So those kind of the parameterization techniques are also available, and some adaptive reduced model, progressive reduced model is also available. As you explore the parameter space, you can adaptively updating your reduced models to maintain the size of the reduced model small enough, but accurately represent the solution as you explore the parameter space. Yeah, I mean, there are so many parameterization techniques out there available, but which we haven't explored all of them yet. We only applied the global ROM so far. Yeah.
Thank you.
You're welcome.
Okay, it seems to me that there are no more questions, so we can thank again Youngsoo for the talk, and we see each other next Friday for the following AJS. Thank you guys for being here with us. Thank you, Youngsoo, for the talk.
Thank you so much.